Thank you, Pat. Thank you for the kind words and introduction. So I can just skip the first paragraph mostly. So I am very interested in my career on the most basic facts of science and nature, but also on the more practical questions of how energy production and consumption affects our everyday life. In particular, I'm interested in the connections between energy, human civilization, and society. 2 months ago, we had a platform here by John Tehan. That was an excellent platform on science and society. And so before my main talk, I would like to add a few thoughts to his presentation from the point of view of a lifelong practicing scientist in basic science and advanced technologies. The most important part, and also probably the most difficult part of a scientist's work, is to keep the facts and findings truthful. Trust, or the lack of trust, in scientific truth really has been very much at the center of the public discourse over the last year during this pandemic. However, this situation is not new at all. In fact, throughout history, truth has always been hard to get by. Lies have always been used to justify oppression and wars and to sow division. The dangers of truth doesn't only apply to scientific facts of nature, but also to the truthful telling of history. It turns out that truth, of course, cannot be proclaimed by an authority, nor can it be determined by a majority vote or by a popularity contest. So how can truth be established? In fact, the answer is at the core of what scientists do. Every discovery or finding is exposed to peers for a very critical review. In essence, truth is determined through a community consensus of knowledgeable and often competing peers. This method is far from perfect, and there have often been attempts to manipulate the process, but it is the best we have at the moment, or maybe ever. So science based on rigorous peer review really has revolutionized the world with this process of establishing reliable truth. The existence and dangers of global warming, for example, pose an enormous challenge to the establishment and acceptance of scientific truth, not just in the general population, but also in parts of the scientific community. The last time I spoke here at the society, I talked about how human society and all of living nature is governed by the flow of energy, and how the discovery of cheap or even free energy in the form of fossil fuels has changed the way we organize life and society. The freely available energy allowed us to implement equality as a basic human right and end slavery and indentured servitude, which actually enabled human civilization for millennia. So global warming, of course, will force us to stop using fossil fuels, and if we can't find another freely available source of energy, the basis of our free, liberal society could be threatened. And this might be another inconvenient truth of global warming. So the existence of human-caused global warming itself was long the subject of politically motivated attacks. It took a worldwide collaboration of climate scientists working over many years with extensive peer review to establish the truth of human-caused global warming. And in fact, we owe these scientists a deep gratitude for doing this, despite being attacked relentlessly. A similar worldwide effort by scientists is needed to develop solutions and mitigations for global warming that is fact-based, fully peer-reviewed, and includes the full life cycle impact of any potential solution. I fear that this is not happening, and we are betting on solutions that might not reduce our dependence on fossil fuels in the future. So, for example, even after investing substantially in renewable energy sources for the last 20 years, the concentration of CO2 in the atmosphere, the main greenhouse gas that is causing global warming, continues to increase faster and faster. So now I want to turn to the main topic that I want to talk about today, namely the deep human wonder about the origin of the world and the beginning of life, and what science can contribute to the story of the origin of the cosmos and us. Most of the information I'm relating here about the origin mythologies I found on Wikipedia. And I want to put in a plug for Wikipedia here. Today, maybe more than ever, we need facts that we can rely on, and this can be very challenging with all the suspicion of authorities. Wikipedia is a community-based effort to provide reliable information to everybody. The editors of Wikipedia are all volunteers, take their mission very seriously, and are using an open process and peer review. Today, Wikipedia is the largest compendium of knowledge in the world, and despite many attacks, misinformation, and attempts of politicizing facts, it is providing a source of factual information that we so desperately need to face all our challenges together. As with the scientific peer review process, here as well, the establishment of truth is a community effort. So all creation stories, in fact, throughout human history, are trying to make sense of our existence and the world around us. This probably reflects our deep need to understand the purpose of our existence and giving it meaning. And the very first question to answer seems to always be, why is there anything? Why is there an earth that is separate from the sky? Why is there solid ground and empty space around us that is itself separate from the waters of the oceans? Also, the oceans were usually assumed to fill up the rest of the cosmos and often assumed to be unstructured, a primordial place where everything started. This was actually quite prescient, since we know now that life in fact started in the oceans. So in many mythologies, Egyptian, Babylonian, ancient Indian, etc., the act of initial creation is the separation of a primordial darkness or chaos into heaven and earth. This is the original and first step to create structure from a watery chaos. It is notable that it's not always a god or gods that create. Some mythologies simply state the act of creation. Most familiar to many of us is the Genesis creation narrative, the creation myth of the Abrahamic religions. This myth was most certainly based on these earlier mythologies. So in Genesis 1, it says, "In the beginning, God created heaven and the earth." An alternative translation, closer to the original Hebrew, is, "When in the beginning God created the heavens and the earth was untamed and shapeless." Again, we see the reference to an unstructured primordial substance. So there seems to be a deep wonder about the process of creating order from disorder or chaos for all of humanity. And it's understood that this process is essential to the creation of the cosmos and to our own existence. This transition from chaos to order is indeed a difficult to understand process, if not an outright mystery. We're all very familiar with the constant creation of disorder from order in our own lives. But how can it be that there to be order from disorder? How can there be structure from chaos? It was always assumed that there must be some divine intervention for this. But it's also a puzzle for the scientific understanding of nature. In fact, one of the fundamental laws of physics, the second law of thermodynamics, very much supports our intuition that disorder has to always increase. There's a name in physics for the level of disorder. It's called entropy. It's such an important concept that it has its own name. The second law of thermodynamics simply says that in a closed system, for example, our home, the Earth, our whole galaxy, or the whole universe, entropy or disorder can only stay the same or increase, but it can never decrease. This seems to forbid the creation of a structure out of chaos, because a structure has much more order than chaos. Here, chaos or disorder is both a uniform or shapeless initial state, the primordial soup, or the end result of the decay of structures. Both states have a high level of disorder or entropy. As we will see later, the solution to this puzzle of how structure can be created is to either increase the disorder somewhere else or to expand the system. For an analog, this is similar to get a clean house by getting rid of stuff, increasing the disorder somewhere else, or building an addition for putting your stuff in. So let me now try to share the screen. Okay, can you see? Okay. So this is what you see here is a depiction of the evolution of the universe since the Big Bang, showing the structures that formed during its long history. And I indicated the times here. This marker here is for 1 second after the Big Bang. This is 3 minutes, 300,000 years, 1 billion years, and here is the present, 13.8 billion years. So the time is stretched out dramatically. We now know that the universe started 13.8 billion years ago with something that resembles a vast explosion. At the very beginning, the universe was filled mostly with pure energy, without any structure. And even today, the universe is still expanding at the speed of light, creating vast amounts of new space every second. The initial evolution of the universe and the creation of the very first structures was then governed by the strongest of the three forces of nature, aptly called the strong force. And in that diagram, that's the period right here. You may not have heard of the strong force. You probably know the other two forces, gravity, the force that holds the Earth and the sun together and also keeps us from floating into space, and the electric force that can generate sparks and lightning. Today, from the strong force, we only see glimpses in the form of the nuclear force. And it's still a very strong effect. It gives the atomic bomb its horrendous destructive power, and it also powers the sun. But the actual strong force, as it acted at the start of the universe, is vastly more powerful than that. The strong force acts directly on the quarks, the most fundamental particles, and also has a very unique feature. It gets stronger as you separate the quarks, so it acts like a spring. So let me see. So this is depiction. This is completely different from how we experience gravity or the electric force, where the force is much weaker at a distance. So here you see three quarks held together by this spring-like force, the strong force, enclosed inside in the proton. So this feature of the strong force meant that once the quarks are pulled together by the strong force into little clumps of three quarks, as is shown there, they essentially cannot separate again, and they haven't done that to this day. These clumps all contain three quarks that keep the strong force bottled up inside these little bubbles, and very little is leaking out. The clumps are called protons and neutrons, and the leaking strong force we today call the nuclear force. This process of initial clumping occurred about 100,000ths of a second after the Big Bang, really immediately after the start. So one could say, in the beginning, God created protons and neutrons. The clumping feature of the strong force defied the march towards greater disorder. So what about the second law of thermodynamics that says that disorder always has to increase? For the whole universe, this still has to be true. However, the universe is expanding so fast, and as it is adding more and more of these shapeless space, which then compensates for the creation of the proton and the neutron structures. So these little clumps of energy, the protons and neutrons, held together by the strong force, also create the mass of these new structures. Mass, our mass, is therefore nothing more than localized pure energy. And we all carry with us 10 billion protons and neutrons. All of them formed 13.8 billion years ago. Let me see. Okay. So the creation of mass set the stage of the second phase of structure creation. Gravity. Gravity pulls one mass towards another mass. Even though gravity is very weak, a very weak force, it always pulls masses together. Nothing can stop it. So over time, mass, protons and neutrons, would accumulate more and more in a second wave of clumping, forming very large stars that ignited due to the nuclear force. So let there be light. And then there was light. The unstoppable gravitational force continued to make larger and larger structures, from solar systems to galaxies, and the picture shows you a typical spiral galaxy, very much like our own Milky Way galaxy, to galaxy clusters, and eventually to black holes. Black holes, by the way, suck in everything in their neighborhood, and they might be the final fate of all structures in the universe. But this is luckily in the far future. So we saw that the nature of the two forces, the spring-like strong force and the unstoppable gravitational force, have created order from the chaotic beginning of the universe. And the rapid expansion of the universe balanced this evolving order with new chaotic space. So that's the solution of the puzzle. Now, how about the final chapter, the creation of life? Life is based on highly structured, highly complex molecules, and life continuously produces more life, more structure. And this all happens in the midst of a constant decay. The whole Earth could be looked at as a closed system, and therefore disorder could only increase. So everything should decay or should never have been created in the first place. So even here, we again face the same mystery or puzzle. Luckily, we have a continuous source of order shining down on the Earth in the form of the sunlight. The light from the sun not only gives us almost all the energy, but it also gives us order on structure by the fact that the light comes from a single location, our sun, the star in the middle of our solar system. Remember that the stars themselves were the structures created by the gravitational force. And now this source for structure is passed on to the Earth to form and maintain life. The Earth, in fact, is importing order and energy from the directional sunlight and gets rid of the order, of disorder, in the form of waste heat by radiating it into deep space, as you can see in this illustration. This is the analog of getting rid of stuff to clean house, the emission of waste heat. So this doesn't explain how life started, but explains why life could exist on Earth. If the sunlight would come from all directions at all times, instead of a single location, a uniform illumination, as most artificial lighting is, for example, life would not be possible. the incoming light and the outgoing radiation would quickly balance, and there would be no way to get rid of waste heat. A localized source of light coming from the sun is therefore critical to life on Earth. So many of the concepts of ancient mythologies, order from chaos, the sun as the origin of life, can also be found in our present understanding of the evolution of the universe and life itself, evolving without divine intervention, but due to the nature of gravity and the strong force. Why these forces are the way they are is a topic of intense studies, but remains unanswered so far. So thank you for your attention.
So that's the conclusion of our program for today. However, if people stay on, they can ask Thomas questions until 12:15, thereabouts. And then we will begin our membership meeting. So you can all unmute yourself if you like. And but I would suggest again that that you raise your hand, preferably electronically, if you want to ask questions, and I will call upon you. So I see a hand from Linda Napoli. Is that correct, Linda?
Correct, Pat. So, Thomas, I was disappointed that your talk ended so quickly because I thought you were going to lead in to talk about how global warming is changing the setup that you described for the Earth receiving the sun's rays, and how are we impacting on all of that with global warming? What exactly is the connection there?
So that is probably a separate talk. But the quick answer is that yes, there is a delicate balance between the light and the energy that comes from the sun and the energy that's radiated into deep space. That's a delicate balance that needs to be maintained and is being disturbed by the greenhouse gases. So less of the energy is radiated off, and that's why we have global warming, right? It just keeps the energy in. So that's the only but very fundamental connection with this picture. Other planets weren't so lucky as Earth was. For example, Venus, those gases increased to the point that they had a runaway situation where the heat just constantly increased and the gases got denser and denser, and now it's extremely hot, not able to support life. That is, in principle, a possible outcome of greenhouse gas accumulation in the atmosphere. That there is a runaway situation. The Earth, in its history, has gone through phases where that actually was the case. Greenhouse gases, of course, didn't come from burning fossil fuels. They came mostly from volcanic eruptions. But you can get to the point where the greenhouse gases are so dense that it's getting much, much hotter. And that itself then accelerates it. So it gives a feedback effect. We got out of that. The Earth obviously got out of this situation, unlike Venus. And I don't quite recall the exact reason how it got out of that. But there is an alternative scenario that the Earth also went through. And that's when most of the Earth is covered with ice. In that case, the light is reflected, and so that has a feedback effect in the other direction. It gets colder and colder, and the heat can't get maintained. And that was also in the history of the Earth. It went through this sort of snowball period. That I remember how why the Earth got out of that, I think it was because of volcanic activities, basically making the greenhouse gases act to warm the Earth and get out of this snowball situation, and the glaciers retracted and it became temperate again. But the period of human civilization is a period of extreme stability, and which hasn't been found in other periods of the Earth's history. So we were pretty lucky, and we should not try to disrupt it with this fossil fuel.
Thank you.
Thank you. We have Sal Capone has a question. If you can unmute yourself, Sal.
Yes, Mr. Roser, thank you for that very enlightening discussion. I'm wondering, from your perspective and your connections with Brookhaven, what is the future of particle research in the United States going forward at this time?
That's very much an open question. So it's this, of course, is not decided by Brookhaven Lab. There are discussions going on in the community. In fact, there is for particle physics, there is a planning effort going on right now, which should conclude probably in 22. I'm involved in that, but not in a very major way. But I do know that on the table is whether there should be another large atom smasher in the US. The US, of course, led the development of accelerators and colliders right after World War II. But then, other places around the world were catching up. And probably the most well-known lab is in Switzerland, at CERN, which now is hosting the largest collider in the world. We are sort of second at Brookhaven, which is not well-known fact, but Brookhaven has the only and largest, the only particle collider in the US at the present time. But the question really is, where should the next collider be? And for me, actually, an even more important question is, can we afford a next collider, right? Not necessarily because of money, but because of the use of energy of these colliders. So I have been active in promoting or proposing a more sustainable way to look at the future of particle colliders. We had some ideas. In fact, we published a paper a little while ago on the next green collider, and it has generated a lot of attention. But even beyond that, I mean, even if you try to make it as green as possible, it's still very expensive and using a lot of power, typically tens, if not hundreds of megawatts of electric power, which my personal opinion is may not be justified. Even though I spent my life in particle physics, I'm not sure I could justify that. Right? So, yeah, it's an open question. And I think, I mean, maybe to your point, it's important that we're all involved everybody is involved in making these decisions. Right.
Thank you. Any other questions for Thomas? Dorcas, if you can unmute yourself,
yeah.
Or you're unmuted, if you can ask your question.
Hi, Mr. Thomas. My question is, I know recently they've been talking about how crypto mining is using a lot of electricity. Is it almost at par with the particle collider?
Yes, thanks for the question. I'm also astonished and amazed by this, what I would consider extremely wasteful use of energy, because nothing good really comes out of that. And I think particle accelerators do actually advance our knowledge, and so I wouldn't consider that as waste, but nevertheless it should be critically looked at. But spending energy on cryptocurrency is the ultimate in waste. Absolutely.
And David Sprinson has a question.
Yeah. Oh, following up from the previous question, Thomas, you know, that which I mentioned to you before, I mean, you are involved with the RHIC, Relativistic Heavy Ion Collider, and that's being transformed. And I don't know what you think about that. I mean, that's a major investment at Brookhaven Lab, starting in, I guess, transfers in 2025, I think is the transition to the electron ion collider. I mean, I don't know if you want to, can you explain a little bit the significance of that, since you were talking about the development of a major particle accelerator? You know, what's the significance of this transformation at Brookhaven Lab?
Yeah, so it very much falls into what I was talking about, namely the present collider, the relativistic heavy ion collider, really studies the early phase of the phase of the universe that predates the formation of protons, when it really was still a soup, right, and an unstructured soup of quarks and gluons being the force particles. And looking at the transition from that to the structure of protons. The electron ion collider, its focus is to look inside the proton, of the existing proton, not the forming proton at the beginning of the universe, but the existing proton today. And what does it look like inside? So I gave sort of an artist view, showed an artist view of that, but that was probably completely wrong, highly simplified. Right? Reality is extremely complicated. The inside of a proton is almost like a world to its own, right? Not connected in any obvious way to us, except through the nuclear force. And even the nuclear force is not something we are aware of in normal life at all. But if you go inside a proton, everything is completely different from our everyday experience. It's sort of, I at times I'm thinking it's similar to being inside a black hole. Right? And inside the black hole, everything is reversed from outside the black hole. It's a completely different world. Now, we couldn't live inside a black hole, but so only our imaginations can get us there. But people have tried to do that, and it is a weird world. And inside the proton, it's sort of similar. A very weird world, and really understanding that, which means really understanding the strong force, because that's where the strong force really acts. That's the goal of the electron ion collider.